Very good evening, students.
Good evening, sir.
Good evening, all of you. So, without wasting any time, let us start with the discussion. Last class we have seen about alkynes, and today we'll be continuing, completing the next part of hydrocarbons, that is aromatic hydrocarbons, and then we'll proceed with the next topic named as haloalkanes and haloarenes. Right? Let us start with the reaction. Like aromatic hydrocarbons, mainly about benzene. Benzene, you have to look at methods of preparation, physical properties and chemical properties, same as all other functional groups, or like alkanes, alkenes, alkynes, and all other functional groups. You have to look methods of preparation, physical properties, and chemical properties. Methods of preparation of benzene, can anyone think of? Last class itself, we have seen one reaction, like cyclic polymerization of ethine. If you consider ethine and try to do the cyclic polymerization of ethine, then you will produce what? In the red hot iron tube or copper tube, the pi electron density will be moving in such a way such that you will get a 6-membered ring and you will get benzene. If you take 3 moles of CH3, C triple bond CH, you will get what, students? 1, 3, 5 trimethyl benzene, which is nothing but mesitylene. Yes or no? You will be getting 1, 3, 5 trimethyl benzene, which is also called as mesitylene. Let us start with the other set of reactions. Like decarboxylation reaction of aromatic acids, soda lime reaction. Decarboxylation of aromatic acid, if you try to do, like in the decarboxylation, what was the reaction mechanism or what was the intermediate? Carbon ion. So you'll be getting benzene, that is C6H5 connected with C double bond O minus Na plus, treated with Na plus NaOH in the presence of CaO. So it will form respective C double bond O minus. C double bond O minus will try to undergo loss of carbon dioxide and generate this type of carbon ion, aryl carbon ion, that will try to pick up the proton. That will try to pick up the proton to form benzene. Yes or no? So sodium salt of benzoic acid on heating with soda lime gives benzene. That is also the second method of preparation of your benzene. First method is the cyclic polymerization. And from phenol, can you think of any method of preparation? Phenol upon treatment with zinc dust. Yes or no?
Zinc.
Yes or no? That will also produce respective benzene reduction of phenol. You try to look at this reaction. What is the major product in this particular case? Methyl benzene, that is COO minus Na plus, that will be lost as CO2, and that CO2 in the presence of soda lime will be lost as CO32 minus, and you will have Na2CO3 and methyl benzene, which is also nothing but toluene. Reduction of phenol, this is what I am talking about. If you try to do the treatment of phenol with the zinc dust in the presence of high temperature, it will form respective benzene, and zinc has a tendency to convert to respect to Zn plus 2, and you will get O minus 2 ions. And this mechanistic approach proceeds through. The mechanism is not required for the reduction or oxidation reactions. You can just understand the mechanism proceeds through free radical path. Proceeds through radical path. Phenol treated with zinc upon high temperature forms respective benzene and ZNO. Phenol is reduced to benzene by passing its vapors over heated zinc dust. Three methods of preparation you have to be perfect with respect to preparation of benzene. Understand this reaction? Here you will get what, students? That OH group, whatever you have, that will be lost, and oxygen is taken by zinc to form zinc oxide ZNO, and you will have toluene formation. You will have the formation of toluene, that is OH will be converted to respect to hydrogen, and zinc oxide is obtained. Right? Physical properties of benzene. If you look at benzene, aromatic hydrocarbons are non-polar molecules and are usually colorless liquids or solids with a characteristic aroma. That is why they are called as aromatic. Naphthalene balls are used in toilets and also for the preservation of clothes. We will be using in our homes also. Aromatic hydrocarbons are immiscible with water because like dissolves in like. Aromatic hydrocarbons are non-polar molecules, so they are going to be soluble in non-polar solvents only. Like non-polar organic solvents only, they are miscible. So like dissolves in like dissolves in like, and they burn with a sooty flame. So these are the respective physical properties of benzene. And the chemical properties of benzene, mainly benzene will be undergoing, because of the electron rich pi electron density present in the benzene, they will be undergoing mainly electrophilic substitution reactions. And many types of electrophilic substitution reactions we can study, like free radical alkylation, free radical acylation, nitration, sulfonation. Yes or no? All those reactions are coming under the category of free radical substitution reaction. Halogenation is also coming to that category only. Electrophilic substitution reaction is the characteristic reaction of benzene and its derivatives. So we have pi electron density attacking the electrophile. If you remember, we have discussed the same type of reactions in GOC, electrophilic substitution reactions. The pi electron density attacks the electrophile. As soon as the pi electron density attacks the electrophile, we get a VLAN complex or sigma complex. So the mechanism goes like this. The pi electron density attacks the electrophile. As soon as the pi electron density attacks the electrophile, we get a positive charge here and electrophile is substituted. Here aromatic stabilization is not present, so the hydrogen CH electron density is lost, and you will be getting aromatic stabilization back. And this hydrogen is picked up by the respective base or whatever the other components which are present in the reaction mixture. Mechanism: pi electron density attacking the electrophile, that is the rate determining step. Rhenium ion or sigma complex or VLAN intermediate, or this is actually resonance stabilized. To regain back the aromatic nature, the nucleophile can, one thing is nucleophile is attacking the electrophilic carbon. This is one possibility you are talking about. The other possibility which you can think of is nucleophile can try to pick up this proton, or you can say base picks up this proton, CH electron density comes into. Out of these two possibilities, which is major and which is minor?
First one is major.
First one is major because that is aromatic nature. Yes or no? Due to aromaticity, the first one is going to be major. You cannot say positive charge, positively charged carbon is there. So nucleophile, you cannot attack that particular carbon. So because that will lead to non-aromatic system. So to regain back the aromaticity, so the proton is going to pick up the CH electron density comes into. This is nothing but the general mechanism for the electrophilic substitution reaction. And in case if you have electron donating group will be ortho-para-directing or meta-directing.
Ortho-para-directing.
Ortho-para-directing, and electron withdrawing groups will be meta-directing.
Meta-directing.
And chlorine, like exception will be there for halogens. If you take halogens, for halogens, inductive effect is dominant or mesomeric is dominant? Inductive is dominant. If you go with that logic, what you should say? Halogen should be
Meta-directing.
meta-directing, but in reality they are ortho-para-directing. In reality they are ortho-para-directing because lone pair of electrons on chlorine, they are also in resonance. But if you compare the reactivity, like whenever you are looking at the position of electrophile, you have to go with the mesomeric effect of chlorine. Whenever you are talking about reactivity of halobenzene towards electrophilic substitution reaction, like simple benzene and halobenzene, which are more reactive towards electrophilic substitution?
Benzene.
Benzene, because inductive effect is dominant in comparing the reactivity, whereas mesomeric is dominant when you are trying to compare the electrophilic substitution. Right? Very good. Note, rate towards electrophilic substitution reaction obviously depends upon nucleophilicity of benzene ring. If more electron density is present in the benzene ring, then only you can attack. If more money you have, then only you can give. And that will also depend upon the stability of sigma complex or VLAN intermediate. After the pi electron density attack, whatever the complex is forming, if that is stabilized, then the attack will be easy. So rate of electrophilic substitution reaction is directly proportional to nucleophilicity of benzene ring, also directly proportional to stability of sigma complex. Like electron releasing group plus M plus H or plus I, benzene, and electron withdrawing group minus M minus H minus I. If you try to compare the order, which will have greatest? The electron releasing group or electron donating group, they will have greatest reactivity. Then benzene, then electron withdrawing group, that is minus M minus H minus I. This is the order of rate of the substituted benzene derivatives towards electrophilic substitution reaction. Rate towards electrophilic substitution reaction for the benzene and its derivatives will be in this fashion. Right, students? Activating groups. Activating groups are those groups which increase the electron density at ortho and para positions. That means electron donating groups. Substituents which make ring more reactive than benzene. Substituents which make ring more reactive than benzene, they are said to be activative. That means rate towards electrophilic substitution reaction is more than benzene. Like if you have any group connected to the benzene, like phenyl, any group connected to the phenyl ring, like plus M or plus H or plus I, and if that group is electron donating group either by inductive effect or hyperconjugation or mesomeric effect, then you can say that is ortho para directing and activating groups. And examples of such groups are O minus, OH, NH2, NH, C double bond O CH3, O C double bond O CH3, CH3, benzene. So all these are electron donating groups or not? All these are electron donating groups if you observe carefully, like NH2OH, lone pair of electrons on oxygen coming into resonance, lone pair of electrons on nitrogen in resonance, NHCOCH3, lone pair of electrons on nitrogen again resonance, O minus, negative charge on oxygen in resonance, O C double bond CH3, lone pair of electrons on oxygen in resonance. Everywhere you have electron donating groups, so all these are said to be activating groups. CH3, if you consider, it is electron donating by hyperconjugation. All these are activating groups which increase the electron density at the ortho and para positions. All activating groups are ortho para directing, directs the incoming electrophile at ortho and para. So you have two possibilities, like ortho and para are getting electron density. So you can get a mixture of ortho and para products. Out of ortho and para, which is major, which is minor?
Para is major.
Para is major. Is that applicable for all the cases, or is there any exception cases?
Exceptional cases.
Exceptional cases, generally if you are talking, para is major because of maintaining minimum repulsions. But in case if the electrophile develops intramolecular hydrogen bonding, then ortho is major. Deactivating groups, substituents which make ring less reactive towards benzene are called deactivating groups. If the ring is less reactive towards electrophilic substitution, that is deactivative. So they have less reactivity when compared to benzene. Benzene is more reactive towards electrophilic substitution than deactivating group. NO2, COH, CHO, CCl3, NH3+, all these are electron withdrawing group. They withdraw the electron density, so obviously they are going to be deactivating the benzene towards electrophilic substitution reaction. Right, students? Note, generally deactivating groups are meta-directing, directs the incoming electrophile at meta position. So whenever we have electrophile, you will be having the meta substitution of that particular electrophile whenever we have a deactivating group. Right? Exception, as I have told you, halogens. Halogens are weakly deactivating, but ortho para directing. Reactivity is controlled by inductive effect, but orientation is controlled by mesomeric effect. As I was saying, this is an exception. If you talk halogens, reactivity towards electrophilic substitution reaction, that is controlled by inductive. So benzene is more reactive when compared to halobenzene. But orientation, that is controlled by mesomeric effect. So rate towards electrophilic substitution reaction, benzene and halobenzene, if you try to compare, benzene will be more reactive. And attack of electrophile will be again happening at the ortho and para position. So both are there. Mesomeric effect and inductive effect both are there. So mesomeric effect will be controlling the orientation of the electrophile, whereas reactivity is controlled by inductive effect, because the net domination is inductive effect. Reactivity rate is depending upon that. The same point I have explained in the GOC as well, if you remember. Is that clear, students?
Yes, sir.
And I have also said one point, like what is the rate determining step in this particular reaction, RDS? RDS is pi electron density attacking the electrophile. So if I take C6H6 or C6D6, is there any change in the rate of reaction towards the electrophilic substitution reactivity?
No, sir.
No, because the cleavage of CH bond, it is happening fastly, so it is not involved in the rate determining step. So even though you think of C6H6 and C6D6, there is no difference in the reactivity rate, because rate determining step is a pi electron density attacking the electrophile. Right, very good. Look at some examples. We'll solve some examples. Compare the rate of following compounds towards electrophilic substitution reaction. A, B, C, D you can think of. A, B, C, D. Give the order.
ABCD.
ABC.
ABCD only because OH is electron donating group by mesomeric, CH3 is electron donating by hyperconjugation, fluorine is electron withdrawing by inductive effect, NO2 is electron withdrawing by mesomeric effect. So phenol, then toluene, then chlorobenzene, then nitrobenzene. That's the right order. Because greater is the electron donation, greater will be the electron in state ortho and para. So greater will be the electrophilic substitution reaction. Try to give the order here. You can also easily give the order here. NO2 groups are electron withdrawing, methyl groups are electron donating. Compound A, both methyls, plus H plus H. Here you can say plus H. Here you can say plus H and minus M. Here you can say minus M. Last M, minus M and minus M. So both electron donation, one donation, one withdrawing, both withdrawing. So obviously rate will be in this fashion. Yes or no? Rate will be depending upon rate of electrophilic substitution reaction will be depending upon the electron density present in the ring. If you have electron donating groups, more will be the electron density in the ring, more will be the rate. If you have electron withdrawing group, less will be the electron density in the ring, less will be the rate. Compare here. Compare the rate towards the following compounds towards electrophilic substitution reaction. Like they were talking about O minus electron donating, NH2 electron donating, OH also electron donating. So if all the three groups are electron donating and by all the three are donating by mesomeric effect, then you have to think of which can donate greatly. Which can donate greatly? The negatively charged species can donate the electron density greatly when compared to neutral. The NH2 and OH are neutral, whereas O minus is negatively charged, so it can donate greatly. First point. When compared to neutral, NH2 and OH, which can donate greatly?
NH2.
NH2 because electronegativity comes into picture. Oxygen is more electronegative. More electronegative atom withdraws the electron density, withholds the electron density. Less electronegative nitrogen that can donate the electron density. So phenoxide greater, then aniline, then phenol. You should not compare oxygen and nitrogen. This phenoxide and aniline, if you are trying to compare, you should not compare electronegativity because here oxygen has negative charge. Negatively charged atom will be a better nucleophile, better electron donating group when compared to neutral atom. Compare here, compare the rate of the following towards electrophilic substitution reaction. Compare students, like A, B, C, D you can think of. Give the order right or wrong. Okay. Suman says A, B, C, D. Suman, but in D we have three methyl groups, right?
Sir, plus H, alpha hydrogen.
Yes, plus H effect. We have to consider that alpha hydrogens. Because if you take CH3 group, the CH electron density comes into C double bond C pi electron density moves away. If you try to write the respective resonating structure, you'll have negative charge developed at ortho, and you have two more CH bonds and one no bond resonating structure, that is C and H plus will have no bond, just an resonating structure is there. So if you consider more number of alpha hydrogens, more number of resonating structures will be there. But if you consider compound D, all the CH3 groups are electron donating, so this is also electron donating by inductive effect only. But in A we have hyperconjugation with the 3 alpha hydrogens, in B 2 alpha hydrogens, in C 1 alpha hydrogen. So here we have 3 alpha hydrogen, 2 alpha hydrogen, 1 alpha hydrogen, 0 alpha hydrogen means here only inductive is operative, not hyperconjugation. Okay, don't confuse with 3 methyl groups. 3 methyl group means 3 electron donating. No, there you have only inductive effect, here we have hyperconjugation. Right, very good. Here CH3 CD3 CD3.
CH3 IS, then CD3, then CT3.
Earlier we have said there is no rate depending there is no dependency of rate on the CH bond. But now again, why you are saying CH3?
So because CH3 will show hyperconjugation while Deuterium tritium bond.
Yes, CH3, CD3, CD3, all if you can think of hyperconjugation, the CD bond has to cleave. To increase the electron density at the ortho position or meta position, the CH electron density that has to be cleaved, right? So which bond can be cleaved easily? CH bond, then CD bond, then CT bond. That we have explained using the reduced mass concept as well. So no, CH3 greater than CD3. If you are talking about a rate of electrophilic substitution reaction with respect to C6H6 and C6D6, they don't depend upon that CD and CH do not depend upon the rate, because CD bond is not cleaved in the rate determining step. But here CH3, CD3, CD3, this CH electron density can be used in increasing the electron density, so that is why rate will be high. Here, which is more reactive towards electrophilic substitution, A or B? Easily answering. You can easily answer this. There are two rings. Which is more reactive towards electrophilic substitution? Ring A, if you consider lone pair of electrons and nitrogen, they will in resonance in ring A. Ring B, if you consider C double bond of pi electron density is in resonance with C double bond with resonance with C double bond C. But C double bond is electron withdrawing. Lone pair of electrons and nitrogen is electron donating. So in ring A, electron density is increased. In B, electron density is decreased. So A is more reactive. A is more reactive because NH is electron donating group. NH group is electron donating group. Compare here, find out the position where electrophile gets attached. OH, NO2, CCl3. If you consider OH, the electrophile can attack at ortho and para positions. NO, because OH is electron donating group, NO2 is electron withdrawing group. Electron withdrawing group means the electrophile gets attached at meta position. CCl3, what type of group? Electron donating or electron withdrawing? CCl3 is also electron withdrawing group. So again, it is going to be meta directing group. So meta position, you will get the electrophile attached. Right? Find out the position where electrophile gets attached. So if we have toluene, obviously CH3 is electron donating group, ortho para directing. Ortho and para positions, you have the increase in electron density. And then you have OH and CH3. OH will be electron donating, CH3 is also electron donating, but OH donates electron density by mesomeric. Methyl donates by hyperconjugation. So OH should be given the high priority. So with respect to OH, ortho and para, you have to consider this is ortho, and this is para. Para is already blocked. So where the substitution can happen? At the ortho positions only, because para is already blocked, right? Then CH3, CH, CH3, CH3. So this is also hyperconjugation. This will also be hyperconjugation, but more hyperconjugation will be with respect to this methyl. Yes or no? With respect to this methyl only, we have 3 alpha hydrogens. Here we have 1 alpha hydrogen. So with respect to this methyl only, electron density position is going to be decided. So with respect to this methyl, these two are ortho and this one is para. Para is already blocked. So ortho is going to be substituted. Okay.
Yes, sir.
Yes, right. Find out the position where electrophile gets attached. CH3, NO2. CH3 is plus H, NO2 is minus M. CH3 plus H, here also plus H. Lone pair of electrons and oxygen, they are electron donating group, whereas C double bond is electron withdrawing. It is electron donating group. It is electron withdrawing group. Look at the position now. It doesn't matter how strong or how weak electron donating group is. The electrophile gets substituted always with respect to electron donating group only. So with respect to CH3 only, electron density is increased at ortho and para. So para is already blocked by NO2. So ortho position gets substituted. With respect to the CH3, this is ortho, this is para. And now steric repulsion also comes into picture or not? With respect to the CH3, this is ortho, this is ortho, this is para. With respect to the CH3, this is ortho, this is also, this is para. So at all these three positions, electrophile can substitute. But if you think of this particular position, you will have slightly more repulsions. Okay, slightly more repulsions, because electrophile, the two methyl groups are present closely. And the third group, the electrophile will substitute the para position, because with respect to oxygen, that is oxygen is electron donating group, it increases electron density at ortho and para. Ortho and para both can be possible, but ortho will have electrostatic repulsions, para least repulsions. Ortho and para are possible, but para will be slightly major because of less repulsions. Ortho will be minor because there is no possibility of intramolecular hydrogen bonding, right? That's why we are saying. Right? Then the reactions, after looking at the reactivity and at what positions the electrophile gets substituted, we can understand about formation of electrophile. So if you think of benzene and treat with an electrophile connected with nucleophile, the pi electron density attacks the electrophile and you have ultimately substitution reaction. Electrophile gets substituted. Hydrogen is going to be connected with nucleophile. Generally, something which is picking up the hydrogen is a base. Although here it has been written as nucleophile, you don't worry. This is actually base. You can think of that base picks up the proton. So the reaction mechanism is simple halogenation reaction. Benzene treated with chlorine in the presence of Lewis acid like AlCl3, we get a chlorobenzene and HCl. What was the mechanistic approach? Cl2 will react with AlCl3 to form Cl plus and AlCl4 minus, first one. First thing is you have to generate the electrophile, students. Chlorine will react with AlCl3 to form AlCl4 minus and Cl plus. Cl plus and AlCl4 minus. This is the transient state you can understand. Because we all know chlorine is a non-polar molecule because a bond is present between two chlorine atoms. A bond is present between two chlorine atoms, so that is a non-polar molecule. AlCl3 is electron deficient. It tries to attract the electron density. So as soon as it tries to gain the electron density, Cl plus is going to be formed. Benzene now will be attacked by Cl plus. Pi electron density attacks Cl plus, and you will get this type of mechanistic approach. AlCl4 minus, which was in the reaction mixture, that will now try to pick up the proton. CH electron density comes into, so that you can gain the aromatic nature, and AlCl3 is produced back and HCl is also released out back along with the substitutionate position, like chlorobenzene is obtained. Yes or no? Electrophile is chloronium ion or halonium ion. Is this reaction clear, students? Yes or no? Halogenation, very simple.
Yes, sir.
Yes. All right. Friedel-Crafts alkylation reaction. When benzene is treated with alkyl halide in the presence of anhydrous AlCl3, alkyl benzene is formed. In the halogenation, can I use FeBr3, FeCl3? In halogenation, FeCl3 in the presence of Cl2 or AlCl3 in the presence of Cl2 or FeBr3 in the presence of Br2 or AlBr3 in the presence of Br2 can be used. But in Friedel-Crafts alkylation, what you have to use? Anhydrous aluminum chloride only. Okay, when benzene is treated with alkyl halide in the presence of anhydrous aluminum chloride, alkyl benzene is formed. What happens when you try to use FeCl3? I have told you that previously.
It's not that strong Lewis base, that's why it does not pick up the proton.
Lewis base or Lewis acid?
Oh, Lewis acid, sorry, sir.
Okay. So it's not that strong Lewis acid, so it can't pick up the carbon chlorine electron density. So electrophile is not obtained. So rearrangements are not possible. So here, whenever you think of AlCl3 reaction, rearrangements are possible. So carbocation forms. So rearrangements occurs if possible before attack on benzene or derivatives. So let us look at the examples, different examples. What happens in this case? Benzene reacted with CH3, CH2Cl. Same, you have benzene, CH3, CH2Cl treated with AlCl3 to form respective CH3, CH2 plus and AlCl4 minus. That CH3, CH2 plus, it will not undergo rearrangements because that is the only stable carbocation possible. So as soon as it attacks, you get CH2, CH3 and a positive charge on this position. Now AlCl4 minus will try to pick up this proton. CH electron density comes into, you get CH2, CH3 plus AlCl3 plus HCl. Okay, so that is a major product. Ethyl benzene and HCl is obtained. and AlCl3 is regained back, that will be reactive with next molecule. Here what will happen, students? Isopropyl benzene will obtain. You will get what? Because the carbocation what is obtained, that will undergo rearrangement. So you get CH3, CH3. Isopropyl benzene is going to be obtained as a major product. You get a carbocation, primary carbocation will rearrange 1, 2 hydride shift. 1, 2 hydride shift can occur. Rearrangement can happen to form a more stable carbocation. That will lead to the formation of isopropyl benzene or cumene. With respect to this isopropyl benzene, can I form phenol? Can I prepare phenol?
Yes, sir.
Yes or no? So we'll discuss that in alcohols, phenols, and ethers. Friedel Crafts acylation. Acylation means we have CH3 C double bond to Cl, acyl halide. The reaction of benzene with acyl halide or acid anhydride in the presence of Lewis acid AlCl3 eats acyl benzene. So what happens in the presence of AlCl3? So you should not get confused, as I have repeatedly told you. CH3 C double bond to Cl plus AlCl3 can form CH3 C double bond O plus AlCl4 minus. Why? Because this is resonance stabilized. It will be having CH3 C triple bond O, oxygen 1 lone pair and a positive charge, and every atom has octet electronic configuration in this resonating structure. So the acyl carbonium ion, whatever it is there, that is resonance stabilized. So pi electron density will attack this acyl carbonium ion, and you will get a C double bond of CH3 substituted, which is nothing but acetophenone. CH3 C double bond O Cl, AlCl3 gives CH3 C double bond O carbon plus AlCl4 minus. Yes or no, students? Is that clear?
Yes, sir.
Right. Look at this reaction. What happens? What happens in this case? It will again, like acid anhydride we have taken. Acid anhydride, again CO bond is going to be cleaved. So that AlCl3 will be trying to pick up the acetate ion. The CO bond will be cleaved. You will generate CH3 C double bond O plus, and that is attacked by the pi electron density of benzene, leading to the formation of like acetophenone. Like benzene is now substituted with C double bond O CH3 group. Yeah, the same compound, whatever they have written here. Benzene substituted with C double bond O CH3 group. And CH3 C double bond O acyl carbonium ion is actually stabilized by resonance. Formation of electrophile method 2, like in the method 1 we have used the Lewis acid, and method 2 you can think of any other substitutions. Yes or no? So we have benzene react with AOH in the presence of H plus ion. It will lead to the formation of A group substituted on the benzene, and H2O is released back. So what is that? What is that AOH? What is that H plus? How the A is attacked? So like whenever we have some acids, how they are going to be undergoing substitution, all the details we'll understand. So nitration reaction, how NO2 plus is obtained. In the nitration, NO2 group is introduced in the aromatic ring. Benzene you are treating with a concentrated HNO3 in the presence of H2SO4. We get nitrobenzene and H2 is released. Mechanism, HNO3 in the presence of H plus, it forms NO2 plus and H2 and HSO4 minus. How the reaction happens? HNO3 will have this structure N double bond O, OH, and we have H2SO4, S double bond O, S double bond O, OH and OH. H2SO4 can easily, it is a better acid, so lone pair of electrons and oxygen can pick up this proton. OH electron density can be given to oxygen, forming N double bond O, NO. Oxygen used its lone pair to form a new bond. Already one OH bond is there. Another OH bond is formed. So oxygen has seen the net loss in electron density, so positive charge. And we have S double bond O, S double bond O, OH and O minus. Here this will undergo loss of water to form NO2 plus and NO2 plus H2O plus HSO4 minus. So these are the species present when H2SO4 reacted with HNO3. H2SO4, whenever it is reacted with HNO3, you get NO2 plus H2O plus HSO minus. This is the electrophile. That electrophile will be substituted on the benzene ring. Nitronium ion NO2 plus is substituted. If KHSO4 is added to the reaction mixture, rate of the reaction decreases. Why? Because if I add KHSO4, SO4, HSO4 minus ion will be a common ion. If HSO4 minus is a common ion, this dissociation will be decreased or not due to common ion effect. So whenever you are trying to do the reaction, common ion effect, why you are saying? Because KHSO4 is going to be a strong electrolyte which produces K plus ion and HSO4 minus ion. Although we say H2SO4 is a strong acid, there exists an establishment of equilibrium. H2SO4 gives H plus and HSO4 minus ion. So weak electrolyte, the dissociation of weak electrolyte is going to be decreased because of the presence of common ion. So H plus ions are going to be decreased. So reaction will not move in the forward direction. So rate of electrophilic substitution decreases whenever you add KHSO4. Is that point clear, students? Simple?
Yes.
Yes, sir.
Sir.
Yes. Try to understand. We are doing the nitration. So we have C double bond O group, O group. So oxygen is electron donating group. CO is electron withdrawing group. With respect to electron donating group only, substitution should happen. Electron withdrawing group decreases the electron density. So with respect to electron donating group, we can have substitution at ortho as well as para. But ortho substitution will lead to repulsions, whereas para will have less repulsions. So para will be major. On the para position, you have electrophile substituted. What is the electrophile? NO2 plus.
Hello, doctors.
Okay. So NO2 will be present at the para position to maintain minimum repulsions. So or maximizing stability. Here where the NO2 is going to be substituted, concentrated HNO3 and H2S4 excess we have taken. Excess, whenever you take excess, what happens? Excess means
At all of
like
them are
all the positions we will be having, like at the both the ortho positions as well as at para positions, we will be having the NO2 substitution. That is nothing but TNT, trinitrotoluene, which is an explosive yellow solid. Okay, that means using chemistry we can actually produce lot of explosive as well. So whenever you have taken toluene and treated with concentrated HNO3 in the presence of H2S4 excess, you will get a trinitrotoluene, which is an explosive yellow solid, Next reaction, sulfonation reaction by concentrated H2S4 or oleum. So what happens in this case, students? What happens in this case? Electrophile, what is the electrophile? SO3 you can take as electrophile. SO3, H2SO4 plus SO3. It is nothing but oleum. SO3 is the electrophile. So pi electron density is going to attack the sulfur. So whatever the pi electron density you have, and SO3 will have S double bond, S double bond, S double bond. So pi electron density will attack the sulfur. The pi electron density present in S double bond that will move away to oxygen. As soon as that reaction occurs, we have sulfur connected with the two double bond O's and SO minus, and we have SH bond here, CH bond here. That CH electron density will be picked up by O minus. So you'll get what? You will get S double bond O, S double bond OH. This is going to be obtained. That is SO3H is going to be substituted, which is nothing but sulfonic acid. You can take just H2SO4 also. You can take H2SO4 plus oleum also. Even though if you take H2SO4, SO3 is going to be produced. That is what. That is why we can say SO3 is a electrophile. Either you take H2SO4 alone, or if you take oleum also. So SO3H, benzene sulfonic acid is obtained. So H2SO4 will be reacting with in the presence of H plus, that is another molecule of H2SO4 will form OH, S double bond O plus H2O. That means lone pair of electrons and oxygen attack H plus. So we have SO3H and OH2 plus. As soon as this bond is cleaved, you get SO3H with a positive charge on sulfur. That SO3H will be now converting into SO3 plus H plus ion. So electrophile here is going to be, you can take SO3 or SO3 with a SO3H with a positive charge on sulfur. Both are same. Right, students? You can understand the mechanism in this fashion. Then alkylation reaction by alcohol. Can you think of this reaction? Alkylation reaction. Can you think of what happens whenever you treat benzene with alcohol? Benzene, whenever you treat with alcohol in the presence of some acid medium, what happens? What will happen? Because alcohol treated with H plus, lone pair of electrons on oxygen, they will be attacking H plus or not? CH3OH, lone pair of electrons on oxygen, they will be attacking H plus. As soon as they attack, what happens? You will get CH3, OH2 with one lone pair on oxygen and a positive charge. That will undergo loss of water to form CH3 plus. That is the electrophile. That electrophile is going to be substituted, leading to the formation of toluene. Toluene and H2 is obtained. Mechanism is same. ROH attacks H plus to form ROH2 plus, which will undergo cleavage to form R plus and H2O. Carbocation is formed, right? R plus is formed. Here we have taken CH3 plus, so no rearrangements. If we have a bigger carbocation, then rearrangements can be possible. Carbocation is formed, so rearrangements can occur before the attack on benzene or derivatives. Because the carbocation is formed, it can rearrange to form more stable carbocation, and then the reaction can happen. Right, students? Important points: vinyl and aryl halides cannot be used as halide components in Friedel-Crafts alkylation. That is true. Why? Like if I want to do a Friedel-Crafts alkylation, I have to take benzene and CH2 double bond CHCl treated with AlCl3. So AlCl3 will react with this particular vinyl halide to form CH2 double bond CH plus, but it is unstable or not?
Yes, sir.
So the vinyl carbocation is unstable. Aryl carbocation cannot be formed because carbon halogen bond exhibits
Resonance.
carbon halogen bond exhibits partial double bond character or not?
Yes, sir.
Aryl halide and vinyl halide you cannot take, because aryl halide, if you take, the carbon chlorine bond cannot be cleaved because of resonance of lone pair of electrons on chlorine with the pi electron density, where carbon halogen exhibits partial double bond character. Because of that partial double bond character, the bond cannot be cleaved. Vinyl halide will form vinyl carbocation, which is unstable. So in that case, no reaction happens. So benzene treated with a CH2 double bond CHPr AlCl3, no reaction. Or PHCl AlCl3, again no reaction. This is a point which you need to understand, because vinyl and aryl halides will not be forming stable carbocations. And polyalkylation is a major problem in Friedel-Crafts alkylation. What is the major problem in Friedel-Crafts alkylation? Polyalkylation. Why? Why? Because if you try to do the Friedel-Crafts alkylation, you always end up with a mixture of products. Why? Because whatever the methyl is going to be substituted, that is electron donating group, because of, when compared to benzene and methyl benzene, which is more reactive, students? If you compare benzene and methyl benzene is obtained, right? Methyl benzene is electron donating group by hyperconjugation. So it is even more reactive towards electrophilic substitution reaction. It is even more reactive 2 plus H groups. Yes or no? So when you try to look at the products obtained are more reactive towards electrophilic substitution when compared to the reactant. So whatever the Friedel-Crafts alkylation you are doing, that will never lead to the formation of only single product. Rather, you always end up with a mixture of products. Why? Because the products are more reactive when compared to reactants. Why? Because in the products you have more number of electron donating groups, which increase the electron density greatly. Right, students, let us proceed further. In the presence of strongly deactivating groups, what are those groups? Meta-directing groups, NO2, COH, CHO, NH3 plus. Friedel-Crafts reaction, alkylation and acylation, does not take place. If we have a strongly deactivating group, so we have very less electron density present in the benzene ring. Because of that, a strongly electron withdrawing group, so no electrophilic substitution reaction will happen. Example, if we take nitrobenzene treated with CH3Cl in the presence of AlCl3, there won't be any free radical alkylation happening. because NO2 is a strongly electron withdrawing group. Nitrobenzene can be used as solvent in the Friedel-Crafts reaction. So when you try to look at this reaction, like halobenzene treated with CH3Cl in the presence of AlCl3, halobenzene will be ortho-para-directing. CH3Cl and AlCl3 will produce electrophile. What is the electrophile? CH3 plus and AlCl4 minus. The CH3 plus is going to be substituted ortho and para positions, where para is going to be major. Para will be major. We can use nitrobenzene as a solvent because nitrobenzene will not undergo Friedel-Crafts alkylation reaction. If a nitrobenzene can also undergo Friedel-Crafts alkylation, how can you use that? Because that will lead to the different other set of products. Are you getting this logic or not? The nitrobenzene, since it will not undergo Friedel-Crafts alkylation because it is a strongly electron withdrawing group, you can use that as a solvent to perform Friedel-Crafts reaction for halobenzene. Okay, these are the some of the important points which you need to understand with respect to these electrophilic substitution reactions. Next point, Gattermann-Koch reaction. What is Gattermann-Koch reaction? Can anyone remember? Gattermann-Koch reaction. Benzene plus a CO plus HCl in the presence of AlCl3 or CO2Cl2 will form respective benzaldehyde. How is that going to happen? Simple. CO, the carbon monoxide, whatever you have taken, since there is a coordinate bond from the oxygen towards the carbon, so you can say electron density is given to carbon from oxygen. So oxygen will be getting a positive charge and carbon gets a negative charge. So you have to treat carbon monoxide as C triple bond O, carbon negative, oxygen positive. This are treated with HCl. Hydrogen gets partial positive, chlorine gets partial negative. The carbon will try to pick up the proton, so we get a CH bond, C triple bond O, oxygen has a positive charge. So to neutralize the positive charge, the pi electron density moves towards oxygen. As soon as it moves, you get a HC double bond O with a positive charge on carbon. This will act as an electrophile. Benzene treated with a HC double bond O with a positive charge that gets substituted. You get C double bond O H. Same electrophilic substitution reaction, but electrophile generated here is HC double bond O with a positive charge on carbon. This is nothing but your Gattermann-Koch reaction. This reaction you can understand carefully. Same electrophilic substitution reaction. And in this reaction, we are actually preparing the benzaldehyde. Benzaldehyde is obtained in this particular reaction mechanism. Okay, HC double bond O, carbon bearing positive charge, treated with benzene, it will form respective benzaldehyde. Gattermann aldehyde synthesis. Gattermann aldehyde synthesis. What is this aldehyde synthesis? And what type of, like benzaldehyde again produced, but now we are treating with a different set of reagents. Benzene treated with HCl in the presence of HCl and AlCl3. After that, acidic hydrolysis produces respective benzaldehyde. How is this going to happen? Like first, what is the mechanistic approach? Like electrophile, what type of electrophile is obtained? HCN treated with HCl. In HCN, we have lone pair of electrons present on nitrogen or not? In HCN, we have lone pair of electrons present on nitrogen. That lone pair of electron present on nitrogen that will be attacking the hydrogen. So it will lead to the formation of HC triple bond N. Nitrogen used its lone pair to form a new NH bond. So nitrogen gets a positive charge and chloride ion is lost. In this reaction, nitrogen bearing a positive charge is unstable because it is more electronegative. So C triple bond and pi electron density will be given to a nitrogen. So you get the hydrogen connected to carbon. Carbon double bond nitrogen, NH bond, nitrogen regains its lone pair. Carbon will get a positive charge now. HC plus C double bond NH. That is the electrophile. This is the electrophile. And we have benzene. And what is the electrophile? HC plus double bond NH. Electrophilic substitution you can do because it is benzene. You can substitute any carbon atom because there is no other group. So you get CH double bond NH present. Yes or no? You will get what, students? Whenever you try to do this first reaction, since electrophile is HC plus a double bond and nitrogen bearing a positive charge, nitrogen bearing a lone pair and NH, you get a CH double bond NH, imine systems are obtained. This upon acidic hydrolysis forms benzaldehyde. How we are going to do the acidic hydrolysis of imines? So it is going to be attacked by H plus ion. Lone pair of electrons and nitrogen attack H plus. They will form what? Benzene is going to be present as it is, like C6H5, single bond CH, double bond NH, right? Now that double bond as it is, nitrogen, one NH bond already present. The nitrogen used its lone pair to form a new NH bond. So what charge will be accumulated on nitrogen now? Nitrogen used its positive charge will present on nitrogen. Earlier, if you look carefully, carbon and nitrogen, we have a double bond. The pi electron density is moving towards nitrogen. That's okay because nitrogen is more electronegative than carbon. But H2O, is it a good nucleophile? No. H2O is not. H2O can act as a nucleophile, but it is not a great nucleophile. So to make the nucleophilic attack of water on this carbon atom, we have to increase the electrophilicity of the carbon. Why I am doing the acidic hydrolysis? Why not I am directly doing the hydrolysis? Because I want to increase the rate of this reaction by increasing the electrophilicity of the carbon. How I can increase the electrophilicity of the carbon? I want to move the pi electron density away from carbon greatly. So instead of lone pair of electrons and nitrogen, if that nitrogen possesses a positive charge, the movement is great now. So H2O now comes into scenario. So lone pair of electrons present on oxygen on the water, they will attack the carbon. So C double bond and pi electron density moves away. So as soon as this attack occurs, we get a C6H5 connected with carbon, CH bond as it is. Now carbon and nitrogen will have a single bond. Nitrogen has a lone pair and two NH bonds as it is. Carbon now connected with the oxygen, new bond is formed. Oxygen has two lone pairs, now only one lone pair. And two OH bonds are present on oxygen earlier, same now, but one of the lone pair is lost. So oxygen gets a positive charge. Positive charge on oxygen, is that stable? No. So OH electron density is moving towards oxygen. So because OH electron density is moving towards oxygen, can I say partial positive charge is developed on hydrogen? Because of the development of partial positive charge on hydrogen, can I say lone pair of electrons on nitrogen can easily pick up this proton? This OH electron density will be given to oxygen. Ultimately, what happens? You get C6H5 as it is present. This carbon is now connected with a CH bond, also connected with oxygen. Carbon CH bond as it is also connected with oxygen. Oxygen regain its lone pair, two lone pairs and one OH bond. And nitrogen used its lone pair to form a new bond. So nitrogen will have three NH bonds now. And nitrogen's lone pair is lost in the new attack. So nitrogen gets a positive charge. Nitrogen getting a positive charge, is that stable, students? No, it withdraws the electron density. So lone pair of electrons and oxygen comes into. As soon as they come, the CN electron density is given to nitrogen. So we get what? We get C6H5 connected to carbon. Carbon now already has CH bond. It is now connected with C double bond O. Oxygen earlier has two lone pairs, now only one lone pair, and OH bond as it is and a positive charge. And NH3 is present. NH3, which was present in the reaction mixture, we have lone pair of electrons and nitrogen. And this oxygen bearing positive charge is unstable. So OH electron density is moving. So lone pair of electrons and nitrogen picks up the proton, forming C double bond OH plus NH4 plus ion. NH4 plus reacts with water and stays as NH4OH. Is that clear or not?
Yes, sir.
Okay. I'll just erase. I'll just add this extra slide by removing it 1 second, so that whatever we have written now, that will be staying. Okay, so this was the exact mechanism, exact mechanistic approach for the formation. Right, students. So this is nothing but your Gatterman aldehyde synthesis. Earlier Gatterman-Koch reaction. Then oxidation using strong oxidizing agents. What are the strong oxidizing agents? KMnO4 in the presence of H plus, KMnO4 in the presence of OH minus upon heating, K2Cr2O7H plus. Yes or no? So these are your strong oxidizing agents. So whenever you have benzene ring connected with the carbon, which is connected with either hydrogen or pi bonds or oxygen, and when you try to treat this with strong oxidizing agents, you will get either benzoic acid or benzoate ions. The mechanism is not required. These are strong oxidizing agents. Strong oxidizing agents. Mechanism is not required. What happens? The benzene ring connected with carbon, where carbon is connected with a hydrogen or pi bond or oxygen, that will be converted to respect to COOH or CO minus, COH or CO minus. So we have benzene ring connected with CH3 oxidizing agent. We have respect to COH substituted. Oxidizing agent is either KMnO4 or K2Cr2O7. What happens in the second case? Ethyl benzene treated with same oxidizing agent. What you will expect? Benzene ring is connected with a carbon, where carbon is connected with hydrogens or not. So directly you get COH. Here what happens? Benzene ring is connected to carbon. Carbon is connected to methyl groups, 3 methyl groups. No hydrogen, no pi bond, and no oxygen. So obviously what happens? No reaction happens in this case. Are you getting this? Are you getting these points or not? These are very important. The oxidation of alkyl benzenes. These are nothing but oxidation of alkyl benzene. Oxidation of alkyl benzene will form respect to benzoic acid. When the alkyl benzene, the carbon connected to benzene ring, that should contain a pi bond or a hydrogen or an oxygen. Like if I take this reaction, CH2OH, this will also be converted to respect to C double bond OH whenever I treat with KMnO4 in H plus. Okay. So the carbon connected to benzene ring, if it contains the oxygen or connected to hydrogen, or it is involved in pi electron density, pi bonding, then that will form respect to benzoic acids. And if you are doing the reaction in the basic medium like KMnO4 in the presence of OH minus upon heating, then you will get respect to benzoate, because basic medium means the C double bond OH acid, that OH bond is there, right? That is also going to be cleaved because we have basic medium. Right? What happens in this case? C6H5 C triple bond CH treating with some oxidizing agent. What happens? It doesn't matter, I have told you, right? Pi bond or oxygen or hydrogen. Mechanism is not required. Directly carbon triple bond is going to be lost. You will get C double bond OH. Benzoic acid is obtained. Next example, benzene connected to CH2, CH2, CH3, that is propyl group, and CH2OH. This carbon is connected with hydrogens. This carbon is connected with hydrogens and oxygen. So both the carbons are going to be oxidized. So we'll get what? COH, like hexane 1,2 benzene 1,2 dicarboxylic acid. Yes or no, which is nothing but phthalic acid. Both are going to be oxidized because connected with 2 hydrogens. Pi bond is there, hydrogen and hydrogen comma oxygen. Here benzene is connected with carbon. Here we have carbon connected with 2 hydrogens. Here we have carbon connected with 2 hydrogens. So those 2 hydrogens, the carbon is connected with hydrogens, so they are going to be undergoing respect to oxidation. You get C double bond OH, C double bond OH. Again you get same benzene 1,2 dicarboxylic acid. Benzene 1,2 dicarboxylic acid is obtained. Is that clear, students?
Yes, sir.
These are important. Like whenever you get a dicarboxylic acid, the dicarboxylic acid, you can do different other sets of reactions also. And how can we prepare dicarboxylic acid? 1,3-dicarb. You know HVZ reaction? Anyone know HVZ reaction? Remembered? Hell-Volhard-Zelinsky reaction.
Cl2 in the presence of phosphorus.
Yeah, what happens, Suman?
In the nearest carbon of COOH group, Cl will be added.
What is the mechanistic approach?
Don't know, sir.
Okay, fine. We'll discuss that. So what happens means we'll have this type of reaction, right? CH3, CH2, C double bond OH, Cl2 in the presence of red phosphorus followed by hydrolysis. We'll get CH3, CHCl, C double bond OH. And now can I convert this carbon chlorine bond to carbon cyanide? Can I treat this with KCN? You can generate CH3, CHC triple bond N because KCN produces K plus and Cn minus will form C double bond OH. This can I do acidic hydrolysis? Acidic hydrolysis of cyanides produces what? CH3CH, C double bond OH, C double bond OH. 1, 2, 3, 1, 3 dicarboxylic acid. Can I heat it or not? Like I can use this compound as A. Like compound A is propanoic acid treated with a Cl2 in the presence of H2 produces B. This is your B. B treated with KCN produces C. C treated with H plus and H2O produces D. D upon strong heating produces what? 1, 3 dicarboxylic acids. You know this logics or not? 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. 1, 2, 1, 3 acids will lose water, lose carbon dioxide. 1, 4, 1, 5 will lose water. 1, 6, 1, 7 will lose CO2 and H2O. Okay, this is what reaction happens. Like 1, 3 carboxylic acid means what? COH, COH, nothing but oxalic acid. 1, 3 oxalic acid, malonic acid. Oh my such good apples, succinic acid, glutaric acid, adipic acid, pimalic acid. If you take COOH, COOH, it is nothing but what type of acid? 1, 2 acid, right? 1, 2 acid will undergo loss of water, loss of carbon dioxide. CO2 is lost. So you'll get a HCOOH plus CO2. 1, 3 acid is what? Malonic acid. That means you'll have CH2, COOH, COOH. This is 1, 3 acid. Again, CO2 is lost. You get a hydrogen and CH3, CH2 are connected. So you get CH3, COOH plus CO2. So 1, 2, 1, 3 acids will undergo loss of carbon dioxide when you heat them. 1, 4, 1, 5 will undergo loss of water when you heat them. They form cyclic anhydrides. They form 1, 6, 1, 7. They undergo loss of carbon dioxide and water where they form cyclic ketones. Only cyclic anhydrides of 5-membered or 6-membered rings are going to be formed, which is nothing but Planck's rule. Planck's rule says what? Planck's rule says only cyclic anhydrides of 5 or 6-membered rings will be formed. If you have higher cyclic anhydride of 7-membered ring, that is never formed. Rather, whenever you take 1, 6 dicarboxylic acid, there you will be having the loss of water as well as carbon dioxide. The mechanistic approach we will discuss in the carboxylic acids and derivatives. Okay, students. So that means these dicarboxylic acids or similar to that can be obtained whenever you use HVZ reaction, oxidation reactions. All these are useful for us. Oxidation using V2O5. Whenever you try to oxidize using V2O5, V2O5 in the presence of 300 degrees Celsius, you will get phenol. Benzene treated with V2O5 at 300 degrees Celsius, phenol is obtained. Benzene treated with V2O5 at 500 degrees Celsius, you get maleic anhydride. All of you note down, mechanism is not required for this reaction. You have to remember, benzene treated with V2O5 at 300 degrees Celsius produces phenol. Benzene treated with V2O5 at 500 degrees Celsius produces maleic anhydride. like maleic acid is obtained, from that loss of water is going to happen. You will be generating maleic anhydride. At high temperature only this reaction is happening. Carcinogenicity and toxicity. Benzene and polynuclear hydrocarbons contains more than two benzene rings fused together are toxic and said to possess cancer producing or carcinogenic property. Okay, this is very dangerous. Such polynuclear hydrocarbons are formed on incomplete combustion of organic materials like tobacco, coal, and petroleum. They enter into human body and undergo various biochemical reactions and finally damage DNA and causes cancer. Okay, these are very important. Like tobacco is highly dangerous, coal and petroleum. That's why mines, the people who are working in mines, they are also exposed to different dangerous scenarios. They are all toxic. Okay, hydrocarbons are fused benzene rings. They are going to be toxic and they are formed by incomplete combustion of organic materials. And they can damage the DNA, deoxyribonucleic acid. In DNA, what are the three groups present? Phosphate ring,
base,
sugar, and
nitrogen
base. Yes or no? Different types of bases are there. Purine bases, pyrimidine bases, all that we'll discuss. So once the DNA is going to be gets damaged, and ultimately you will be generating cancer. So that is highly dangerous. And some such molecules are given here. You have to just note down them. Note down in sense, you don't need to note down in notes. Just understand. I'll be sharing it, sharing the PDF handouts. Okay. So there are some molecules like this 3-methyl cholanthranine. So benzanthracene, 1256 dibenzanthracene. Yes or no? These molecules are going to be carcinogenic in nature, that is cancer producing. Try to solve this question, last question. You have treated benzene with Cl2 in the presence of AlCl3, Cl2 excess AlCl3, Cl2 in the presence of UV and 500 degrees Celsius, 500 Kelvin. What is going to happen in all cases? Cl2 in the presence of AlCl3 benzene, what will happen?
chlorobenzene,
Chlorobenzene.
Will obtain. That is very simple. Halogenation reaction. Cl2 excess AlCl3. Cl2 excess we have taken. Cl2 excess we have taken, right? So at every carbon atom, the substitution is going to happen. You will get hexachlorobenzene C6Cl6. Cl2 in the presence of UV at 500 degrees Celsius. What happens now? First thing is chlorobenzene. Whenever you take Cl2 excess and AlCl3 is there, then you will get all the carbon atoms are going to be substituted with the electrophile Cl plus. That will lead to the formation of hexachlorobenzene C6Cl6. But whenever you treat with Cl2 in the presence of UV and high temperature 500 Kelvin, what happens is the pi electron density is going to be broken. You will get all the carbon substituted with chlorine and pi bonds are also broken. So you get C6H6Cl6, which is nothing but benzene hexachloride. Yes or no? C6H6Cl6 obtained. Hexachlorobenzene C6Cl6 is different. Here, whenever you have Cl2 in the presence of UV, you have the cleavage of pi bonds also. That is also called as gamaxene or lindane. That is earlier used as insecticide, but later again it has been found that it is toxic in nature. Is that clear or not?
yes,
Yes or no? So these are the different points which you need to understand carefully in the hydrocarbons. Just a second, we'll start with the next chapter. And how are you people feeling about organic chemistry? So no response.
A bit hard, sir.
A bit hard. So only thing in organic chemistry is you just need to practice more. Okay. All the mechanisms are also discussed along with the normal points. If I just discuss only the point like what is substrate, what is the product, what are the conditions, you can't even sit in the class for one day if we teach organic in that way. We do have reactions where you have to remember some points, where you have to, like oxidation reactions we have, KMnO4 oxidation. If I want to teach the mechanism for KMnO4 oxidation or H2CrO4 oxidation of respect to alcohol to respect to carboxylic acid, it will take one class. So there are some very complex reactions whose mechanisms are not required. But if every reaction, if you are just remembering rather than understanding, so finally you will feel difficult. Okay. Only thing is you try to practice more, allocate more time. You will enjoy it for sure. Okay. Most of the questions you are answering, just a continuous practice will be taking you to right places. Okay. All the very best. You don't need to think like it is difficult and all. Next chapter, students, haloalkanes and haloarenes. The replacement of hydrogen atoms in the aliphatic or aromatic hydrocarbon by halogen atom results in the formation of alkyl halide and aryl halide respectively. That means if you try to replace the hydrogen by a halogen atom, whatever the resulting compound you get, that is nothing but your haloalkane or haloarene. Yeah, Suman is sending some reactions and all. What happened, Suman?
No, sir, by mistake only.
Okay, okay. Okay, we have an alkane, students. From the alkane, you are trying to replace the CH bond and you are replacing the CH bond with a halogen. So haloalkanes and haloarenes may be classified as follows: C2H5X, CH2X, 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 CHX, CH2X. That means based on the number of halogen atoms present in the compound, you will be getting a respective name for that particular halogen. Like if you have C2H5X, only one hydrogen is replaced, so it is said to be monohaloalkane. Two hydrogens replaced, so you get a dihaloalkane. Three hydrogen replaced, so you get a trihaloalkane. So classification of haloalkanes and haloarenes based on number. Very simple classification. If I try to replace one halogen, one hydrogen with one halogen, that is said to be mono. Two hydrogens replaced means di. Three hydrogens means tri. More than that means poly. Okay, monohaloarene, dihaloarene, as well as trihaloarenes are obtained. So one halogen atom replacing the hydrogen atom in the arene system. Two halogens and three halogens doing the same produces monohaloarene, dihaloarene, and trihaloarene. Monohalo compounds may be further classified according to the hybridization of carbon atom to which halogen atom is attached. Like halogen, only one halogen attached, it is monohalogenated compound. Again, the halogen is connected to one carbon, right? That carbon's hybridization, based on that, we again do the classification. So first set of compounds is compounds containing sp3 hybridized carbon connected to your halogen. So in that you come to the category of alkyl halides or haloalkanes. In alkyl halides, halogen atom is bonded to an alkyl group. Like RCH2X, halogen atom is bonded to an carbon atom which is sp3 hybridized, and it can again be classified into primary, secondary, and tertiary. So halogen is connected to carbon. Carbon is connected to only one other alkyl group, so primary. Halogen is connected to carbon, where the carbon is connected with the two other alkyl groups, so secondary. Halogen is connected to a carbon where carbon is connected with three other alkyl groups, so it will be tertiary haloalkane. Is that clear or not? Classification 1 based on number of halogen atoms present in the molecule. Next classification of monohalo compounds is the halogen atom is connected to a carbon which is sp3 hybridized or sp2 hybridized? sp hybridized carbon will not be connected with halogens because both are more electronegative in nature. sp hybridized carbon is electronegative as well as halogen is also more electronegative. So such bonds are not formed. If the carbon is sp3 hybridized, sp3 hybridized carbon connected to halogen, in that case you have alkyl halides where they are again classified into primary, secondary and tertiary. Allylic halides also comes under this category because you have CH2 double bond CH, CH2Cl. So chlorine is connected to a carbon where the carbon is sp3 hybridized. These are nothing but allylic position or allylic carbon. Halogen atom is connected to a carbon which is allylic carbon or allylic position. Similarly, we have benzylic positions also. Benzylic halides means these are the compounds in which halogen atom is bonded to sp3 hybridized carbon atom next to aromatic ring. Like we have CH2X, this is nothing but your benzylic, and that benzylic carbon is also sp3 hybridized. So carbon atom, if it is benzylic carbon, then it is said to be benzylic halide. If the carbon is allylic carbon, allylic halides. Yes or no? If halogen connected to a carbon which is allylic carbon means allylic halides. If it is benzylic means benzylic halides. So like that the classification has been done. Compounds containing sp2 hybridized carbon connected to halogen. Aryl halides or haloarenes. Aryl halides or haloarenes means you have halogen atom directly connected with a benzene ring. These are the compounds in which halogen atom is bonded to an sp2 hybridized carbon atom of an aromatic ring. These are the compounds in which halogen atom is connected to or bonded to sp2 hybridized carbon atom of aromatic ring. These are all nothing but your aryl halides. Vinylic halides means what? Halogen is connected to the carbon, which is vinylic carbon. What is the vinylic carbon? The carbon present in the carbon-carbon double bond system, that is said to be vinylic carbon. So these are the compounds in which halogen atom is bonded to sp2 hybridized carbon atom of carbon-carbon double bond. So this is a vinylic carbon to which halogen is connected. So vinylic halide. Vinylic carbon to which halogen is connected. So vinylic halide. Is everything clear so far or not? The classification.
Yes, sir.
Yes or no? It's like what are allylic halides, what are benzylic, what are vinylic, what are arylic, what are the alkyl halides, primary, secondary, and tertiary, that we have seen. And from methods of preparations of haloalkanes, same type of reactions, same type of study, methods of preparation, properties, physical properties and chemical properties. We will be studying the same for all types of functional groups, starting from alkanes to the last amines also we will be doing the same. By halogenation of alkane, so this reaction will come under which category? CH3 plus X2 in the
Free
presence
radical.
of free radical substitution reaction. What is the rate determining step in free radical substitution reaction? Generation of
Subtraction of hydrogen.
abstraction of hydrogen to generate methyl radical or alkyl radicals. So first reaction is very simple. Free radical, this is nothing but an free radical substitution reactions of alkanes. Free radical substitution reactions of alkanes produces respect to alkyl halides. Along with that, HCl or HX is produced. And in this reaction, there's a possibility of dihalogenation or polyhalogenation. So that is why this is not a suitable way or preferred way to prepare haloalkanes. Second, you have by hydrohalogenation of alkane. By hydrohalogenation, CH3, CH double bond CH2. That is addition of halogen acids to alkanes. What is the mechanistic approach? First step is the rate determining step. What is that step?
Carbocation
Carbonation.
Very good. Formation of carbocation, pi electron and STADAX H plus. You get respect to carbocation, more stable carbocation you have to form. So 2-degree carbocation. Yes or no? The 2-degree carbocation, like you have the reaction in this manner. CH3, CH double bond CH2, HX. Pi electron and STADAX H plus. Loss of halide ion. generating CH3, CH plus CH3. This X minus will try to attack this particular carbon, generating CH3, CHX, CH3. Okay, that is nothing but addition of halogen acids to alkenes forms respect to halo compounds. And we have seen different cases. Since a carbocation is formed, rearrangements are possible, ring expansions are possible, ring contractions are also possible. By halogenation of alkene, right? This is not alkane, it is alkene. And CH3, CH double bond CH2, X2 in the presence of CCl4 forms CH3, CHX, CH2X. What is this reaction? You need to say. We have studied a lot of reactions, such reactions.
Cyclic halonium ion.
Very good. Cyclic halonium ion. What type of addition?
Syn addition.
Syn.
Syn addition.
No, anti-addition takes place.
Anti-addition. Okay. Since they have given two halogen atoms on same side, you should not confuse syn addition. Okay. Anti-addition occurs. Syn addition example, you can think of Bayer's reagent. Okay, Bayer's reagent, syn addition. And you can think of hydroboration oxidation, syn addition. Cyclic halonium ion is formed, anti-addition happens. And in the presence of non-polar solvent, okay, reaction has to be done in non-polar solvent. If you use polar solvent, what happens?
H2O will react.
H2O will act as a nucleophile that will react. Okay. And in case of conjugated ions, what happens?
1,4 addition.
Very good. Conjugated ions undergo 1,4 addition. Okay. The halogen atoms, they are going to be added on the first and fourth carbon atom. That is nothing but by halogenation of alkene. If you alkenes is treated with halogens in the presence of CCl4, all these things are going to happen. From alcohol, alcohol treated with PCl3 forms RCl plus POCl3 plus HCl. If you remember, every reaction mechanism I have explained or not?
Yes, sir.
Yes, sir.
First reaction, what happens? SN1 or SN2 or SNI?
SNI.
SNI.
SN2. SN2.
SN2, chloride ion which is lost, that will attack in the SN2 fashion, forming alkyl chloride, POCl3 and HCl. Second reaction,
SN2.
SN2 again, chloride ion, like SN2 means inversion occurs. Inversion, here also inversion. Why can't SNI?
Because in both of these, P double O bond is formed, which is much stronger.
It's a good leaving group. Okay, the P double bond which is going to be formed, that is going to be a good leaving group. Here we have PX3. With the help of PX3, we have 3 phosphorus halogen bonds. All of them are going to be replaced. So 3 molecules of alcohol will be reacting. So 3 molecules of alkyl halide will be formed. In case of PCl5, PCl5 will act only as electrophile because of only presence of vacant orbitals. PCl3 can act as electrophile and nucleophile, but in this reaction, it has a tendency to act as a electrophile only, even though it has lone pair of electrons. SOCl2 is SNI. SNI means what happens? Inversion or retention? Retention. If I do the same reaction of SNI in the pyridine, like if I do this reaction, ROH plus
First to
SOCl2
SN2.
in the presence of pyridine, it will form RCl plus SO2 plus HCl only, but you will get SN2. SN2 occurs. Why? Because in the molecule, whatever the H plus is there, that is going to be picked up by pyridine, not the chloride ion. So chloride ion has to attack from the backside only. So SN2 attack occurs. ROH plus HX. What happens? ROH plus HX. Alcohol plus HX. So lone pair of electrons and oxygen attack the hydrogen generating ROH2 plus, and X minus, the halide ion will act as a nucleophile. It will try to attack the electrophilic carbon, generates Rx plus H2O. Here two things happen. The halide ion can attack in the SN2 manner or SN1 manner. When it will attack in the SN2 manner? When the more stable carbocation is formed, like 3 degree or more stable, then SN1 happens. If the less stable carbocation is formed, then SN2 occurs. Okay, we'll just look at the same reaction. So these are the reactions like methods of preparations of alkyl halide from respect to alcohols treated with the phosphorus halides SOCl2HX. And out of all these, which is the best reaction?
Associate.
SOCl2. Why? Because the gases are produced which increase the entropy of the system. Yes or no? Which increase the entropy of the system, thereby also increasing the spontaneity of the reaction, and also they can be removed easily from the reaction mixture. Halogen exchange reaction. Who can explain this reaction? Finkelstein reaction. Preparation of alkyl halides RCl, RBr treating with NaI in the presence of dry stone forms Ri plus NaX. What will happen in this case? RCl, like alkyl chloride or alkyl bromide treated with NaI in the presence of dry stone, they form alkyl halide and NaCl, like NaCl or NaBr. What is actually happening, students, here? Try to think on this reaction and explain. All of you try to think on this particular reaction. Can anyone explain the mechanistic approach? Like why it is happening? No one? Rx, like alkyl group is connected with halogen like chlorine or bromine, and you have NaI, Na plus and I minus is there. The I minus is now going to attack the electrophilic carbon, and carbon halogen bond is going to be cleaved. If you think of that particular reaction only, the I minus is going to be attacking the electrophilic carbon, carbon halogen bond is going to be cleaved. There was a difference in the solubilities of NaX, that is NaCl, NaBr and NaI. NaCl, NaBr, NaI, if you look at the solubilities, the I minus, because of large size, it will not be surrounded by water molecules greatly. So I minus can be attacking the electrophilic carbon easily. Whereas whatever the Cl minus, Br minus which are formed, they are going to be surrounded by water molecules, right? That is why they are not going to attack the alkyl halide again to form the respective alkyl chloride. That is the importance of this reaction. It is not about nucleophilicity alone, it is about solubility. Okay, I minus is a large in size and less surrounded, large in size and thus surrounded by less number of water molecules. And thus it can attack the electrophilic carbon. Electrophilic carbon.
So,
Yes, please.
so but it's happening in dry acetone, right? So how does water come?
We have water in the reaction mixture also. Solubilities we are considering now. Less
Okay.
number of solvent molecules you can think of. Okay. So because of large size, I minus is not surrounded by great number of solvent molecules. Number of solvent molecules write down. So if
Yes,
solvent
sir.
if solvent molecules are not surrounding the I minus can attack the electrophilic center so that alkyl halide is formed. Because this reaction, why it is not happening in the backward way, you have to understand. Why can't the alkyl chlorides and alkyl bromides are converting into alkyl halides? Why can't the alkyl halides react with because NaCl is also there. If I start with RCl plus Na gives us to Ri plus NaCl. Why can't NaCl react with Ri to form RCl plus Na? Because the Cl minus is going to be surrounded by more number of solvent molecules when compared to I minus. So I minus, since it is less surrounded by less number of solvent molecules, it can be acting as a respective nucleophile, and this halogen exchange reaction is going to happen. Okay, Finkelstein reaction produces the respective alkyl halides. Is that clear now? Is that clear to everyone or not?
Yes.
Okay, fine, students. Let us stop the discussion here. So next class we'll be continuing with the next set of reactions. You need to understand all the reactions carefully. Okay, nothing difficult. Just every day you keep your effort, you will be reaching your respective targets. Fine. Thank you all. All the best again.
Thank you, sir.
Thank you, sir.
Sir.